Show that the relation capital R on n cross n defined by a comma b is related to c comma d if and only if a plus d is equal to b plus c. So here relation R is defined on set A, that is n cross n. So relation R defined on set A is equal to n cross n, which containing ordered pairs like a comma b, c comma d, and it is given that these ordered pairs a comma b are the elements related to each other if and only if a plus d is equal to b plus c. And we need to prove that this relation R is equivalence. So R is equivalence means we need to show that R is reflexive, and we need to show R is symmetric, and we need to show that R is transitive. So we can say the relation R is reflexive if for every A belongs to the set A comma A belongs to R, then we can say the relation is reflexive. And for symmetric, if A is related to B, that is A comma B belongs to R, then B comma A must belongs to the relation R. And for transitive, if A comma B belongs to R and B comma C belongs to R, then we need to prove that A comma C also must belongs to R. For A comma B comma C belongs to the set A, and here A comma B belongs to the set A. So these are the basic definitions for the reflexive to prove it. And now the set A is containing ordered pairs. So we need to consider instead of elements ordered pairs. So consider, so I'll consider the ordered pair A comma A. Let us consider A comma A belongs to A. So which implies A comma A is related to A comma A, because we can say that the sum of any two these elements A plus A is equal to A plus A, that is 2A is equal to 2A. So for every A comma A, we can conclude that for every A comma A belongs to A, we can say that A comma A must be related to the A comma A to satisfy the condition here. So therefore R is reflexive. And now for symmetric, let us consider A comma B is related to C comma D, means A comma B comma C comma D belongs to R. So when A comma B is related to C comma D, as per the definition, we can say that A plus D is equal to B plus C. Or this can also be written as B plus C is equal to A plus D. And we know that the addition is commutative, so we can also write C plus B is equal to D plus A. So when C plus B is equal to D plus A, so we can consider when C plus B is equal to D plus A, we can write C comma D is related to A comma B as per the definition given. So therefore, when A comma B is related to C comma D, then C comma D is related to A comma B, we can say that R is symmetric. Relation R is symmetric. And now coming to the transitive, now consider A comma B is related to C comma D. So which implies that A plus D is equal to B plus C. And also C comma D is related to E comma F, which implies C plus F is equal to D plus E. And this C plus F is equal to D plus E we can also write D plus E is equal to C plus F. So this is A and this is B. Now let us subtract A and B. A minus B. So we'll get A plus D minus E is equal to B plus C minus F. So we can write A minus E is equal to B minus F, or this can also be written A plus F is equal to B plus E. When A plus F is equal to B plus E, we can write that A comma B is related to E comma F, because as per the given relation, if A comma B related to C comma D, then A plus D is equal to B plus C. So here if A plus D is equal to B plus C means if A comma B must be related to E comma F. So as per the definition of the transitive, if AB is related to R, if A comma B belongs to R and B comma C belongs to R, then we have A comma C, the first element here and the last element. So A comma B and E comma F is also related to R, and hence we can say that R is transitive. Since the relation is reflexive, symmetric and transitive, therefore we can say R is equivalence relation. So we can conclude that the relation is equivalence, which is defined on n cross n. Okay. Show that the function f from n to n defined by f of n is equal to n plus 1 upon 2 when n is odd and n by 2 when n is even is 1 to 1 is not 1 1 but onto. So here we can just show in the diagram a function is defined from n to n, so that if n is an odd number, if n is odd number, you are getting the image as n plus 1 by 2. If n is an even number, if n is an even number, you are getting n by 2. Now to show that 1 to 1, no two distinct elements will have the same image. That is, for x1 not equals to x2, f of x1 must not be equal to f of x2. For x1 comma x2 belongs to the domain of the function, that is n. So here let us consider, let's take an example. We know that 7 is not equals to 8, but f of 7 is equal to, since 7 is an odd number, so we have to write 7 plus 1 upon 2, which is 8 by 2 is 4. And f of 8 is equal to, since 8 is an even number, 8 upon 2 is equal to 4. So we can say for 7 is not equals to 8, f of 7 is equal to f of 8. Both are giving the same image. So we can say that the function is, for with this example we can conclude f is not 1 to 1. One example is enough to disprove the statement. And coming to the next onto definition says that for every y belongs to codomain, that is n, there exists at least one x belongs to n or n belongs to n, such that f of n is equal to y. So this is the definition for onto. Let us check here. Let n plus 1 upon 2 is equal to y1, because here two categories are there. For n is odd, you are getting n plus 1 by 2. For n is even, n by 2. So let us consider the two cases. For n is odd here, so n plus 1 upon 2 is equal to y1, that is n is equal to 2y1 minus 1, which is an odd form. So that f of n is equal to, since n is an odd number, so we need to write 2y1 minus 1 plus 1 upon 2, which is equal to 2y1 upon 2, which is y1. So first we can say that for y1 belongs to n, for y1 belongs to n, there exists some n belongs to n which is odd number such that f of n is equal to y1. And similarly, let n by 2 is equal to say y2, that is n is equal to 2y2. For n is an even number, so we get this is an even number. And now we can say that f of n is equal to 2 times of y2 divided by, since n is an even, divided by 2, that is y2. So here we can say that for some y2 belongs to n, there is an n which is an even number such that f of n is equal to y2. So we can say that for odd number and even number cases we are getting. So generally we can say that for some y belongs to n, there exists at least one x belongs to or n belongs to n, either odd or even, such that f of n is equal to y, and hence we can say this function is onto. So this function is one, not one to one, but onto. Given A is equal to a 3 by 3 matrix, 1 minus 1 1, 1 minus 2 minus 2, 2 1 3, and B is equal to minus 4 4 and 4, minus 7 1 3, 5 minus 3 minus 1. Find AB and use this result in solving the system of equations. X minus y plus z is equal to 4, x minus 2y minus 2z is equal to 9, and 2x plus y plus 3z is equal to 1. So let's find out AB value. A into B is equal to 1 minus 1 1, 1 minus 2 minus 2, 2 1 3 into minus 4 4 4, minus 7 1 3, 5 minus 3 minus 1. So which is equal to, let's apply row with column. First row with first column we'll get 1 into minus 4 is minus 4, minus 1 into minus 7 is plus 7, and 1 into 5 is plus 5. And the next first row with the second column, 1 into 4 is 4, minus 1 into 1 is minus 1, 1 into minus 3 is minus 3. And next first row with the third column, 1 into 4 4, minus 1 into 3 minus 3, 1 into minus 1 is minus 1. Similarly, in the second row, 1 into minus 4 is minus 4, minus 2 into minus 7 is plus 14, and minus 2 into 5 is minus 10. And next second row with the second column, 1 into 4 4, minus 2, and again here plus 6. And second row with the third column, 1 4s are 4, and here minus 6, and again plus 2. And coming to the third row, 2 into minus 4 is minus 8, minus 7, and 3 into 5 is 15. And again here, second row with the second column, 2 4s are 8, plus 1, and here 3 into minus 3 is minus 9. And second row with the last column, 2 4s are 8, plus 1, 3, and again minus 3. So we can write 7 plus 5 12, 12 minus 4 is 8, 4 minus 4 is 0, and 4 minus 4 is 0, and here 14 minus 10, 4 minus 4 it is 0 again, 10 minus 2 that is 8, and here 8 minus 6 minus 6 that is 0, and here 0, and 9 minus 9 0, and 8 plus 3 minus 3 is 8. So we got AB is equal to, so we can write AB is equal to, if 8 is taken common, you're getting 1 0 0 0 1 0 0 0 1, that is 8i. AB is equal to 8i, or we can write 1 upon 8 times of AB is equal to I, or we can also write A times of 1 upon 8 times of B is equal to I. We know that if AB is equal to I, let me use, as per the definitions, if A into x is equal to I, we can write that x is equal to A inverse. Means x is the A inverse of the matrix A. So similarly, A into 1 by 8 times of B is equal to I. So which implies here A inverse is equal to 1 by 8 times of B. So A inverse is equal to 1 by 8 times of B. Let us use in the system of equations. Now the given system of equations, x minus y minus plus z is equal to 4. So we can write in the matrix form 1 minus 1 1, and the second equation 1 minus 2 minus 2, and the third equation 2 1 and 3. To the variables here x y z is equal to the matrix 4 9 and 1. So it is in the form of A x is equal to, we can say something, C, because 1 minus 1 1, 1 minus 2 minus 2, 2 1 3 both are same A. So we can say Ax is equal to some matrix C. So that x is equal to A inverse into C by matrix multiplication inverse method. Matrix inversion method, we can write x is equal to A inverse into C. And we got the A inverse value is 1 upon 8 times of B. So x is equal to 1 upon 8 times of B into C. So let us write this. X is equal to 1 by 8. B matrix is minus 4, 4 and 4, minus 7, 1 and 3, and here it is 5, minus 3 minus 1 is multiplied with the matrix C, that is 4, 9 and 1, which is equal to 1 by 8 times of, again row with column, minus 4 into 4 minus 16, plus 9 fours are 36, and again plus 4, and the second row minus 28, plus 9 plus 3, and third row 20 minus 27 minus 1, which is equal to 1 upon 8 times of 40 minus 36 is, again here we can write 24, and here 9 plus 3 12, 12 here it is minus 16, and again here 20 minus 1 minus 8. So we got x is nothing but xyz matrix. Xyz is equal to, so 24 upon 8 is 3, minus 16 upon 8 is minus 2, and minus 8 upon 8 is minus 1. So from here we can get x is equal to 3, y is equal to minus 2, and z is equal to minus 1 is the solution. And let us verify in any one of the equations. So let us substitute here. When x is equal to 3, so that is 2 into 3, plus y is equal to minus 2, and 3 into minus 3. So 6 minus 2 4, 4 minus 3 is 1, which is satisfying. So we can conclude that the values x is equal to 3, y is equal to minus 2, z is equal to minus 1 is the solution. Using integration, find the area of the region bounded by the ellipse x square upon a square plus y square upon b square is equal to 1, where a is greater than b. Since a is greater than b, the major axis is along x-axis. So let us consider the ellipse. So this is a comma 0. This is minus a comma 0, and say here 0 comma b, and this is 0 comma minus b. And we need to find the area of this region. Area of the region bounded by the ellipse. And we can also see that this is symmetrical about both x-axis and y-axis, and this ellipse is divided into 4 quadrants, we can say. So this is the first quadrant, so and all quadrants are similar. So even if we can find one quadrant also, it is enough. So we can multiply with 4 times. So area of area of the region bounded by ellipse is equal to, so here we can say 4 times area of the region O, say this is A, B, O. So we can write O, A, B, O, and which is equal to, by integrations we can write 4 times integral 0 to A, and the curve is here y dx. Since x square upon a square plus y square upon b square is equal to 1, so we can write y square upon b square is equal to 1 minus x square upon a square, that is y square is equal to b square upon a square of a square minus x square, or y is equal to b upon a root of a square minus x square. So here we can write 4 times integral 0 to a b upon a root of a square minus x square, or 4b upon a integral 0 to a root of a square minus x square dx. And we know the integration 4b upon a root of a square minus x square integration is, so we can write x upon 2 root of a square minus x square plus a square by 2 sine inverse of x by a over the limits 0 to a, which is equal to 4b upon a, applying the limits here, a upon 2 root of a square minus a square upper limit and plus a square by 2 sine inverse of a by a, this is upper limit, minus lower limit 0 by 2 root of a square minus 0 plus a square by 2 sine inverse of 0 upon a, so which is equal to 4b by a. So here the first term is here 0 and a square by 2 sine inverse of a by sine inverse of 1, and again the second term is totally 0, so we can write 2b upon a, 2b upon a into a square, here sine inverse of 1 is pi by 2, so a get cancelled and 2 gets cancelled, so which is equal to pi ab. So we can say that the area of the ellipse, area of the region bounded by ellipse is nothing but pi into ab, so pi ab square units. Okay, pi ab square units is the answer. Show that the lines x minus 1 upon 2 is equal to y minus 2 upon 3 is equal to z minus 3 upon 4, and x minus 4 upon 5 is equal to y minus 1 upon 2 is equal to z intersect each other. Also find the point of intersection. So the given lines, the first line let us write here, x minus 1 upon 2 is equal to y minus 2 upon 3 is equal to z minus 3 upon 4. Let us consider 2b is equal to some lambda, say lambda, so that any point on the line we can also write x minus 2 is equal to 2 lambda, y minus 2 is equal to 3 lambda, z minus 3 is equal to 4 lambda, that is x comma y comma z, any point on line L1 we can write it as 2 lambda plus 1 comma 3 lambda plus 2 comma 4 lambda plus 3. And similarly the second line, let us consider the second line as L2, that is x minus 4 upon 5 is equal to y minus 1 upon 2 is equal to z minus 0 upon 1. Let us consider to be mu, so that x minus 4 is equal to 5 times of mu, y minus 1 is equal to 2 times of mu, and z is equal to 1 times of mu, or any point on L2, say that x comma y comma z is equal to 5 mu plus 4 and 2 mu plus 1 and mu. And to show that these 2 points are intersecting means the point on the line L1 and the point on line L2 must be equal. So let us verify this. 2 lambda plus 1 x coordinate is equal to 5 mu plus 4, which implies 2 lambda minus 5 mu is equal to 3, and the next y coordinate 3 lambda plus 2 is equal to 2 mu plus 1, which implies 3 lambda minus 2 mu is equal to 1 minus 2 minus 1. Let us solve these both equations. Solving for lambda and mu, minus 5 minus 3, 2 and minus 5, minus 2, so we can write plus 1 and again 3 and minus 2. So this is for lambda and mu and 1. So we can write lambda upon minus 5 and again here minus 6 is equal to mu upon minus 9 minus 2, that is 1 upon minus 4 plus 15. So lambda is equal to, so we can write minus 5 minus 6 is minus 11 upon 15 minus 4 is 11, that is minus 1, and mu value is equal to, you're getting minus 9 minus 2, that is minus 11 divided by 15 minus 4, which is 11, which is minus 1. So mu upon mu is equal to minus 1, lambda is equal to minus 1, we got it. And substituting lambda is equal to minus 1 and mu is equal to minus 1 in the third coordinate, that is 4 into minus 1 plus 3 on the first line equation, third coordinate, that is z coordinate. So we are getting minus 4 plus 3 is minus 1, and similarly in the second line the z coordinate is mu, which is equal to minus 1, both are same. And by substituting the points also we can say lambda is equal to minus 1. So 2 lambda plus 1, 3 lambda plus 2 and 4 lambda plus 3, which is equal to 2 into minus 1 plus 1, that is minus 1, 3 into minus 1, that is minus 3 plus 2 is minus 1, and 4 into minus 1 minus 4 plus 3 is minus 1. Similarly, even if we substitute here, 5 into minus 1 minus 5 plus 4 is minus 1, 2 into minus 1 plus 1 is minus 1, and mu is equal to minus 1, both are same. And the point of intersection is considered as minus 1 comma minus 1 comma minus 1. So we can say that these two lines are intersecting each other and the point of intersection is minus 1 comma minus 1 comma minus 1. Find the shortest distance between the following pair of lines and determine whether they intersect or not. X minus 5 upon 4 is equal to y minus 7 upon negative 5 is equal to z minus of minus 3 upon negative 5, and another line x minus 8 upon 7 y minus 7 upon 1 is equal to z minus 5 upon 3. So these two lines are, this line is passing through the point 5 comma 7 comma minus 3. So let us consider the vector passing through the point whose position vector a1 is equal to 5i plus 7j minus 3k, and this line having the direction ratios 4 minus 5 and minus 5. So let us consider the position vectors of this direction ratios as b1 vector is equal to 4i minus 5j minus 5k. Similarly, for the second line is passing through point 8 comma 7 comma 5. The position vectors, let us consider a2 is equal to 8i plus 7j plus 5k, and having the direction ratios the direction ratios 7 comma 1 comma 3. So let us consider the vector b2 is equal to 7i plus j plus 3k. And now we can also say that the direction ratios, they are not proportional, b1 and b2, and hence we can say they are not parallel, which implies that they are intersecting. So the shortest distance between the lines shortest distance between the lines passing through the points a1 and a2 and having the direction ratios b1 and b2 respectively can be taken as a2 minus a1 dot b1 cross b2 upon mod of b1 cross b2, the whole mod. So let us find a2 minus a1. So a2 minus a1 is equal to 8 minus 5, that is 3i, 7 minus 7, that is 0j, and 5 minus of minus 3, that is 8k. This is a2 minus a1, and mod of b1 cross b2. Let us find b1 cross b2. b1 cross b2 vector is equal to I, j, k. b1 vector 4 minus 5, and b2 vector we can add 7, 1 and 3, which is equal to I times of minus 15 plus 5, that is minus 10, minus j times of 12 plus 35, that is 47, and plus k times of 4 plus 35, that is 40. 4 plus 35, that is 39. 39. So we can write b1 cross b2 vector as minus 10i minus 47j plus 39k, and mod of b1 cross b2 is equal to under root of minus 10 whole square plus minus 47 whole square plus 39 whole square, which is equal to the root of, we can write here 3830. After simplification we got the value 3830. So therefore the shortest distance between these lines is equal to mod of a2 minus a1 is 3i plus 0j plus 8k dot b1 cross b2 is minus 10i minus 47j plus 39k divided by root of 3830. After further simplification we got it. So minus 30, and here it is 39 8 times. So 240 plus 72, that is 312, divided by root of 3830, which is equal to 312 minus 30 is 282. So we can say 282 divided by root of 3830 is the answer. The shortest distance is 282 upon 3830 is the answer. And also we can conclude that since the direction ratios are not proportional, and hence we can say that they are skew lines which are not intersecting. So these lines are not intersecting because they are not parallel.